Good evening, everyone. We are in the week 7 problem solving session of the course Digital Controlling Switchboard Power Converters and FPGA-based Prototyping. Week 7 is about Introduction to Verilog and Simulation using Xilinx Webpack. Let me share my screen. Can you see my screen?
Hi, sir.
So we are in the week 7, which is about Introduction to Verilog and Simulation using Webpack. So we'll discuss about Verilog coding and also how to use the Xilinx ISC tool or software to implement the Verilog coding. I am Tejogola, a third-year research scholar working under Dr. Santanu Kapat at IIT Kharagpur. So before we go into week 7 outline, let me briefly summarize what we have discussed in week 6, which is digital control implementation and FPGA-based prototyping. So in week 6, we have started with ADC and DAC. So we have discussed why do we need or where do we need, so what are their requirements, and we have discussed about different ADC architecture. So I have discussed about something called dual slope ADC and how we can get an SAR ADC as well as flash ADC. So this is a parallel ADC, and we have discussed these are series, and we have discussed the trade-offs between them. And in the DAC architectures, we have discussed about R2R ladder DAC, how does it work, and how can we get the output relation with the bits. And in current sensing, we have discussed multiple current sensing architectures. To start with, first we have discussed non-isolated. In that we have discussed inductor TCR and resistor sensing, and then high side sensing as well as low side sensing, where we will use with sensing, and high side is used for peak current mode control and low side is used for valley current mode control. So we have discussed the reasons, and in isolated current sensing, I have shown current transformer as well as something called LM sensor. So we had some discussion regarding the working of the LM sensor. How do we get the information of output, where to see the number of turns, everything we had discussed in this, and I have provided the data sheet as well. And then we have quickly summarized Hall sensor. And then we have gone into buck and boost power stage design. So we have discussed what type of capacitors are available, and what type of inductors are available, and why do we need gate drivers, and what is the functioning of gate driver, the mainly bootstrap capacitor. So we have discussed on these aspects, and then we moved on to the digital control FPGA. So I have shown the FPGA board, and I have shown two codes. First is the LED operated using switch, where when I click the switch, LED will turn on, and the second one is LED blinking. So I have written a code which will run forever, and LED will keep on blinking. So there are 8 LEDs, so sequentially they'll blink only one LED at a time, and then we have solved quickly few problems also based on the concepts that we had discussed last week. Now coming to week 7. So week 7 is from week 1 to week 6 we have discussed about different architectures, sampling techniques, MATLAB simulation, validation, different small signal model, large signal model, which DT model we should use, and what are the ADC architectures and DAC architectures. So to summarize, I can say that if you break this course into 2 parts, one is week 1 to week 6, now week 7 to week 12. So this is mainly simulation based. So I can say simulation, modeling, and analysis. So we had done different types of analysis, and we had done different types of modeling: state space modeling, large signal modeling, small signal modeling, which model is more accurate, which model we should use, and then MATLAB simulation as well as validation. So I can say simulation plus validation. So we have a question: sir, can you upload today's video on tomorrow? Due to some personal problems, I cannot attend the live session. Yeah. So by tomorrow evening, I'll try to upload this video in the YouTube, so you can go through this. I'll try to upload. So simulation plus validation also. But from this week on, we are moving into the actual hardware. Thank you. Okay. So from week 7 to 12. So before we go into hardware, we need to know how to write the code because we are dumping the code in the FPGA. Right? So first we'll learn about Verilog, and then we'll learn about Verilog implementation of different architectures. To start with, we'll start with voltage mode control, which these are in the upcoming week. So this is in the week 7, Verilog introduction. So week 7. These in the upcoming weeks we'll discuss about voltage mode control, current mode control, pulse skipping, modulation, constant on time, constant off time, and multi-mode, all these things. So from week 7, it is very crucial that you learn each and every aspect of the concept. So this week is like a building block for the upcoming week. So whatever we will be using in week 8 to 12, that is simply Verilog coding. So you should be thorough with the Verilog coding. And in this today's session, I'll briefly summarize what Sar has covered, and then we'll quickly move on to the simulation where I'll show the live demonstration and we can have more discussion on the simulation part. So the week 7 outline is as follows. So first I'll discuss about Verilog. So just a basic introduction to Verilog and what is a module. So what is a module and what type of design flows are available in Verilog, and what is the difference between. So every coding language will have data types. So what data types are there? What are we going to use in this course? And different modeling and description styles are available in Verilog, and which will follow. What are the trade-offs? What is the basic difference between them? And just like C, here also we have some expressions and operators. So we here also will discuss what type of expressions are available and what type of operators we can use in ripple carry, and then we'll move on to the Verilog implementation of ripple carry adder. So here we will summarize or discuss about basic Verilog coding, using which we'll move on to the ripple carry adder. So this is again a 4-bit what Sar has discussed in the class. So I'll quickly demonstrate the Verilog implementation, and then we'll move into ISim simulation where I'll show the simulation part of this adder. Then binary numbers. So there are different representation of binary numbers. Maybe you might have studied in your C language as well, but we'll again discuss it in brief. So one is straight binary, other is 2's complement, other is offset binary. So what is the difference between these two and which one we will be using, and how to write this in Verilog. So like you might be knowing these concepts, but the main intention is to correlate with the Verilog. So in Verilog simulation also we can use all these kinds of representation of binary numbers. So how does it change, what measures we have to take while writing the code? And all I can say is this is the most crucial part or most important part in this week or in the upcoming weeks, which is fixed point arithmetic as well as Q format. So this Q format is the most important point or most important concept which you should understand very clearly. So what is Q format? Why do we need Q format and how? So there are several questions. What is Q format? Why do I need Q format? How do I know the Q format? And how to write it in Verilog code? So many questions will arise. We'll discuss about that. And then Sar has discussed the counter-based DPWM. So I'll show the Verilog code. Then again, the simulation, ISim simulation, which is Xilinx ISC, whatever you have installed. I hope you have installed. And then we'll quickly solve a few problems. So to start with Verilog HDL. So as you know, we are going to use Verilog throughout this course. It is mandatory for you to learn Verilog, but you don't have to learn in deep. So whatever that is a part of Verilog which will be used in this course, only that has been taught. So you don't have to learn too much in detail. So whatever that has been covered, in week 7, that is sufficient for this course. But it does not include the entire Verilog. So a part of Verilog which will be used for this course or which has been used for this course was taught in this week 7, which should be sufficient in order to go through all the codes and understand the implementation, all these things. So whatever the Verilog that has been taught by Sir, that is just a part. It is not the Verilog. So this is not a Verilog course. So we have only taught whatever that is necessary for this course. So if you actually want to learn Verilog, then you can register into the Verilog NPTEL, but this is just a part of Verilog, which should be sufficient. So it has multiple concepts. One is design flow, data types, modeling, as well as description styles. So to start with, so introduction to Verilog. So as you know, HDL means hardware description language. So we are actually describing the hardware using code. So the simulator will understand our code, and it will describe the digital circuits in gates, CMOS gates and gates or gates. So the basic building blocks are gates. Using those gates, we will develop whatever logic we want to use, and you need a language to write in the simulator. So there are several such languages, hardware description language. One is Verilog HDL, which is quite famous. Other one is VHDL. We are going Verilog because it is easy to learn and it is widely used in the industry as well. That's why we are going for Verilog, and in this course we do not discuss about VHDL. That is another hardware description language, but Verilog is very useful if you want to apply for placements. Also, Verilog would be very useful, and VHDL also. But Verilog is much easier to learn, and it is widely used in the industry as well as institutes also. So in HDL, we'll describe circuits at RTL level, which is the register transfer level, which is the lowest level of abstraction. And on top of it, we'll write our codes, and the simulator will realize the circuit. So whatever codes we'll write, so simulator will convert that into a hardware circuit. And when we load the code into FPGA, whatever simulator has understood and made that circuit, that will be dumped into the FPGA, and the FPGA will in the simulator. And there are several synthesis tools that support Verilog HDL, and one that we'll be using in this course is Xilinx ISim. So throughout this course, this software will be used. Please kindly install if you have not installed, and if you have installed, and please try to start writing the code. As you know, any coding language you can only understand when you start writing the code. Understanding the concept is different, and writing the code is different. So there might be a lot of mistakes that you'll be making throughout the process, which will help you to understand the language in a better way. So you should start writing the code. So all the codes that Sar has discussed, you can write it and see how the output is coming. I will also be discussing how to use the software. So if you have any doubts at that point, you may ask me. And for post logic synthesis also, many fab vendors use Verilog HDL. So it is quite popular hardware description language. So the typical design flow is as follows. Say if I want to write a code for ripple carry adder, and if I want to implement in the FPGA, first I have to specify my design, and then I have to describe it behavioral. So say Sar has discussed that ripple carry adder, Sar is using multiple full adders, and full adders will consist of different half adders. So first I have specified my design, and then I have to describe this behaviorally. So to my understanding, I have fixed how am I going to write in the Verilog code. So I have fixed that. Now you have to write the hardware description language. So now our architecture is fixed. Now we have to implement this in the Verilog using whatever syntax that Verilog suggests us, and then we have to dump it in the FPGA. So if you realize that it is not working properly, then it means there is a mistake in the Verilog code. So you have to modify accordingly, and then load the code into FPGA and check. So last week, whatever I have shown, I have written the first I have fixed my aim. I want to blink the LED. Then I have seen how I should write the code, and accordingly I have written the code and I have loaded. So in the beginning, I had made a mistake. So I have realized that there is a mistake with my code. So I have again modified my Verilog code, and I have checked in the FPGA whether it is working fine or not. And then I have shown you the modified Verilog code. So there are two types of approach of design. One is the top-down approach, and the other one is bottom-up approach. So just to summarize, say if we are talking about ripple carry adder only. Say this is ripple carry adder, the top level block, which consists of several full adders. So first I'll write the code for ripple carry adder, then I'll write the subblocks of full adder, then I will write the full adder code, which will contain half adders. So I'm coming from the top point, right? So now after writing full headers, I'll write the half header, and half header consists of uh, gate level, so that I'll write in the half header. So this is top down. We are coming from the top. So the hierarchy is coming from the top. Now, if you do from the bottom approach, so now you will write the half header. So at the end of the day, we are implementing the same logic, but the way we are approaching to design it, it matters, like whether we are coming from the top or whether we are going from the bottom. So whatever way is comfortable to you, you should follow that. Usually top-down approach will be easy because we want a ripple carry adder. So we know that ripple carry adder consists of 4 full adders. So then it would be easy for you to go with this approach, but you are free to choose any design approach. So this completes the approach of design. Now we'll come to the module. So in any coding language, so we'll write inside a module. So in Verilog also, we'll be writing the code inside a module, and it is named as module. So this is our one Verilog code block. So this is, you can say, Verilog code block. So this is what we call module in Verilog. So it has some inputs as well as outputs. So this module is used to describe a block in Verilog HDL. And say I have a module here. This is my module. I have written multiple codes of lines, and I'll call another module here. So this is my another module. So this will call another module. And another module also, I'll write the code separately. So now this code should be written separately. The code should not be written inside here. So other modules cannot be described in the given module. So you can call other modules, but you cannot describe them in the this module. Say I'm writing ripple carry adder. I'll call full adder. So this is full adder. I'll only call full adder. I cannot write full adder code inside this. So this is another module. This is another module. So another module code you cannot write inside this module. So we are calling this. Now this will call another half header. So now let me change the color. So now this will call the half header. So what we are doing, we are instantiating a module within the other module. So I'm writing it modular level. So my main code consists of 4 full headers. Each module will call this full header code, and here I have each full header has 2 half headers, which will call this half header code. So every time when we write a module, it starts with module and module name, and you have to write the code, and then it ends with end module. I'll come to an example in the next slide. So each module can have input ports, output ports. So you have to define all the input ports as well as output ports. So you have to define which is input, which is output, what type of input, what type of output, what is the size of the input, what is the size of the output. So let us consider a very basic block, which is half header. So I have 2 inputs. So these are the inputs, and there are 2 outputs. So these are the outputs. So S is nothing but a XOR gate of A and B, and this is an AND gate of A and B. So this Sir has discussed. I will quickly summarize. So this is how to start a module and end module. So whatever names that are there as a code, you cannot use any such names to name this. This name is module. So I cannot name this module as module because that is a instruction for Verilog, which will be always understood by the simulator as a module. So you cannot name this module as module. So we have to name it otherwise. So I have named it half header. HA stands for half header. Here I have described all the ports. These are the ports, but now I have to describe or define which is input. So I have defined A and B are input, and S comma C are output. And if you are using small a, you have to use small a throughout. It is same in any coding language except few coding languages. So now I need S, which should be XOR gate. So XOR again is an instruction. The code will understand this as XOR gate. So only this should be used whenever you want to access that gate. So I have called XOR gate. I have to name the gate, and I have to give this is the output, and rest of them are inputs. So this is the syntax for everything. like when it comes to the gate. So the first one is output and the other two are inputs. So now the code will realize that there is a XOR gate whose output is S and whose inputs are AB. And there is another AND gate whose output is C and whose inputs are AB. So that's how I define half adder.
Sir, in the module HA, don't we need to declare in order of output and input, or we can do it anyway behind HA?
Yeah, so there is a way that you can define inside these brackets also, or you can do it inside the code as well.
Okay, like if I write as HA, A comma B comma S comma C, is it true then?
No.
And the remaining code?
See, HA comma, there will be this syntax input S comma input A comma input B. So you see, this is a module that I am writing. So the Verilog will not know which is input or which is output. But these two lines are already there in the Verilog, already available in the Verilog. And this is a syntax that you have to follow in order to access or use those gates.
Okay, sir. Sir, in Verilog, like which only just gates are defined?
Gate level. So the basic building blocks are gates. On top of gates, we are developing.
Okay, like XOR, like which are available, sir, predefined in Verilog?
XOR gate, AND gate, NOR gate, NOT gate, OR gate, all these are available. All building blocks.
Okay.
But there are different, like say, if I want A and B, I can use this operation also. So, and like G2, C comma A comma B, we also give C as AB. I can also use this operation to do AND. So it is up to one's comfort, whichever way they want to use. We'll come slowly to this part. Okay, so this is about module. Now, as I have discussed here, see, I am calling the full adder in ripple carry adder, but ripple carry adder here they have some variables, here they have some variables. It doesn't have to be the same variables. So how do I call? There are again two ways. You can call them by ordered list, or you can call it by name. So let me give one example. So full adder. Full adder has two half adders, as you know. So S, C, A, comma B, comma C, C. Here there are different variables. If I use this format, then my order should be same. Here S1 will be treated as S. So this will be treated as this. And my C1 will be treated as C. So order should be always followed. This is A and this is my B. If you invert B comma A, then whatever B that you have given will be taken as A here. Whatever A that you have written will be taken as B. So order should be same. That's why we call it ordered list. So order should be same. Here I am using a different variable. Here I am using a different variable, but they will be mapped. So S1 will be mapped to S and C1 will be mapped to C. A will be mapped to A. B will be mapped to B. In the second line of code, HA, this is for HA1. Now, if you come to HA2, S will be mapped to S. So this I'm mapping with this again. S will be mapped to S. C2 will be mapped to capital C. S1 will be mapped to A, and C in mapped to B. So here the order is the crucial thing. If you mess up the order, then the code will not be correct. So it needs the exact same order. So the Verilog will map accordingly. Then is there any solution if I don't want to give the same order? Then there is another way of connecting the signals, which is by name. So here what happens? So here we will tell the Verilog which port should be connected. In this case, here Verilog is connecting the ports. Verilog is connecting the ports by the order. So whatever order we write, it will directly connect. Here we are specifying the order. So we are giving, or we are specifying the connections. So which port should be connected to which port. If you see outside, so it is like dot x of y. So this y is this local variable, and this x is the variable in that module. So what we want S1 to be mapped to S. So I have written S1 mapped to S, and C should be C1 should be mapped to C. So C1 should be mapped to C, and A should be mapped to A should be mapped to A, B should be mapped to B should be mapped to B. So this S1 is in this code, this C1 is in this code, this A is in this code, this B is in this code. So whatever that we are writing dot S, dot C, dot A, dot B, those are in the half adder. So those are in this. So I am telling that S1 in this code is S in this code. C1 in this code is capital C in this code. A in this code is A in this code. B in this code is B in this code. Similarly, here S to S mapping, C to C. Now say here they have written dot S of S1 comma dot C of C1. I can also write dot C of C1 comma dot S of S1 comma dot B of B comma dot A of A, because I am specifying the connections. So I can write in any order, but whatever that you want to connect, these two should be correct. So I can write C first, or A first, or B first. Here you can write in any order as you are telling which ports are connected. So as long as this port to port specifying the connection is correct, you can write whichever one you want to write first. So here it will be less prone to make mistakes. Here you should be careful. That is the only thing. So this is all about connecting different ports. So and specifying which one is connected to what. So I am audible, right? Hello.
Yes, sir, you are.
Okay.
Yes.
Okay. So now coming to data types. So Verilog has data types similar to other languages. One is net and one is register. So what is the difference? Net means it is continuously driven. So the data will be continuously changed if the input changes, and it cannot store any values. So it cannot store any values. So if the input changes, output will change, and it cannot store. Say if I wanted to store a value for some time, it cannot store. It will be continuously driven. And one such, there are so many examples under net. One that we'll be using is wire. So if I want to define something, say wire X, I'll define. So now again, this is scalar because it does not have any size. Now here I have defined Y320, Y, which is a vector. So Y is a vector and it is also a wire. Here X is a scalar and it is a wire. So X will be continuously driven and it cannot store any values. Can you tell me what is the size of Y?
4 bits.
Yes, right. So this 3 is the MSB and 0 is the LSB. So Y is 4-bit wire. And the bits are Y of 3, Y of 2, Y of 1, Y of 0. Similar to C, we'll start with 0. And say if it is N bit, the maximum will be N minus 1, and the minimum, or the LSB, maybe I should say MSB and LSB. So this is N minus 1, the minimum is 0. So it varies from 0 to N minus 1. So if I say Y of 3, I'm accessing that single bit, the most significant bit, similar to again C. So we can individually access it, or you can, if you want to access, you can access it as a whole Y. So it again depends upon how you want to write the code. So this is the net, and the other important data variable is, data type is the register. So as you can see, register, it can hold the value. So it is not continuously driven. So it will be either event driven. So we'll come to that point. What is event driven? So for the time being, you can say event driven. So it will be driven by an event. Until that event comes, it will hold the value irrespective of whether the input has changed. If you want it to hold the value until some other event comes, it can hold the value. So depending upon our use, either we'll use net or we'll use register. So it has different examples. One is reg, one is integer, and one is real, one is time. So this will not be using in this code in this course. So the one that we'll be using is reg, and reg and while will be synonymously used throughout this course. Again, I'm representing or defining two variables which are reg. So I'm writing reg a comma b, and these are scalars. And again, if I want to do a vector, I have to specify the size. How many bit is C? C is of how many bits?
6 bits.
6 bit, yes. So it is Y5 or C5, C4, C3, C2, C1, C0. And always this is MSB and this is LSB. Okay, so this is all about data types. So now coming to expressions and operators. So there are so many expressions and operators that you can use in the Verilog. So these are logical operators. Say if I want to write if A and B. So what I mean to say is if A and B. So when A and B is 1, then it will enter this if loop. If A and B is not 0, then it will enter the else loop. So for logical, we use and. So this is and this is or. So A or B. So if I write A or B instead of A and B, if I write A or B. So if A or B is 1, then it will enter if, else it will enter the else. And this one is not. So not is for a single element. So we will write it as if not A. So if not A means A bar. If A bar is 1, then it will enter if, else it will enter the else loop. So these are few logical operators where you can incorporate these in your code. And these are relational operators. You can say these are also like logical operators only, the first two. So equal to, again, I can write if A equal to B, then some code, else some other code. Similarly, A equal to B, we can have A not equal to B. So actually these should be logical operators. So these are the logical operators that you can use. Now, or you can also say relational operators because we are checking the relation between A and B. So now again, if A less than B, or if A greater than B, or if A is greater than or equal to B, or A is less than or equal to B. So these are some of the conditions that you can use, which are available in any language, and they are also available in Verilog. So if A is greater than or equal to B, then it means 1. So if 1, so it enters the if, else it will enter the else. So you will be writing a code within the if loop, also under the else. So if the condition holds true, then it will enter if, else it will enter the else condition. And similar to other languages, here we have arithmetic operators. So as you know, this is multiplication. So the first one is multiplication, and this is division. So division will not be used in this course. And this is addition. Addition will use, subtraction we might use, multiplication will use, and this will give the remainder which will not use. So we might use these three in the course, and others you can use, but we will not be using in this course because as our code might not require them, so that we don't want to use them also as it is not under our requirements. Now unary or bitwise reduction. So this is unary plus or arithmetic plus. So I can add bit by bit, or I can add a vector. So scalar is also possible, vector is also possible. Here also scalar is possible, vector is possible, and. So I can write C is equals to A and B. So it is bitwise operation. So bit of A and bit of B, they will be doing AND operation, and it will be given to C. Now, what if C is not a scalar? What if C is a vector? say I have written C is equal to and A is equal to 1101. So C will do is 1 and 0 and 1. So in this case, C is 0. Say my A is 1111. My C will be 1. So this is also a reduction. So we are reducing a vector to scalar. And this is how you write. So and A means and of all bits of A. So A is n bit. So we are doing and operation of all the n bits, and the output, which is a single bit, a scalar, will go into B. Similarly, we can do OR operation. So it will do OR of all the bits of A. Similarly, we can do XOR. So it will do the XOR of all bits of A. And we can do NAND, NOR, XNOR operation also. So this is AND. If I put negation, then this will be NAND. And this is OR. So this will be NOR. And this is XOR. So if I put this will be XNOR. So if I want to invert A, then I'll use negation A. So this is not A. There is less than a minute. So if this meeting ends, kindly rejoin the session so we can continue our discussion. So these are some of the operators. Other operators are bitwise operators. So here, as I have mentioned, we are doing A equal to C and B. So these are bitwise operators. So you can either do bitwise or you can do reduction. Similarly, I'm doing C. This is what? NAND. So the same can be done NAND. So if you are doing between 2 bits, it will be A and B. If you are doing for a single one, it will be A. So I can write C equal to A and B, C equal to A. So here it is bitwise. Here it is reduction. So depending upon what your A is, it will perform that operation. Now, again, this is left shift operation, right shift operation. So this is like question mark. C is equal to some select question mark. If select is true, C equal to A. Else C equal to. So where are we? So we are discussing about this operation. So C select. So if select is true, C equal to A, else C equal to B. And this is called concatenation operation. So concatenation operation. Say A equal to 1101, B equal to 01. If I write C is equals to A comma B, then it will concatenate 110101. So this is concatenation operation. And if you use 2, then you can do multiple. So you can replicate. So A is a 110. I'll do B is equals to 3 times of A. So it will concatenate A with A with A 3 times. So B is nothing but this can also be written as A comma A comma A. So we are concatenating A with A. So it will be 110, 110, 110. So this is again an operation which if you want to use, you may use, or like, but for information, you should know what are the operators that are available that we can use. And coming to modeling, so there are 2 types of modeling. Yes.
Sir, in lecture there is like A triple equal to B is expression is there.
So
A triple equal to B.
So if
you have it mentioned here, I guess.
Okay, I don't know. I have to check. A triple equal to B. So what did Sir say about that?
He didn't said anything, but in the slides it is mentioned that if it is identical something, it was written there.
Okay. I'm not sure about that. So like we use A double equal to check if A is equal to B, then it becomes 1. I'm not sure what happens if A is triple equal to B. I have to check it.
They meant
Actually,
like in the slides
I think
it is mentioned.
there is a mistake there, sir, because this is also represents same identical.
Yes. So I'm not sure about that exactly. So if you want to check whether A is equal to B, similar to C, we'll write if A is equal to B. But if you want B to be copied into A, so you use A equal to B. And there are other ways for this also that will slowly come into that. But I'm not sure about A triple equal to. I'll check and I'll get back to you maybe. This is asked by Banerjee, right?
Yes, sir.
Okay,
Yes.
I'll check and I'll get back. So we are completed the expressions and the operations. Now different types of modeling. So a code can be written in different ways. So structurally is the low level of abstraction. So here we are writing in gate level. Behavioral is higher level of abstraction. So we here will not go to will not go to gate level, because every code, if you go into gate level, it will be very difficult, right? So we will not go into gate level here. We will describe the algorithm. So we will tell the Verilog what we want to do. So what is the logic for our code, or say for our circuit, what is the logic? We'll write in higher level of abstraction, and the Verilog simulator will decide how it should be described in terms of gates. But here we are writing the code in gate level. So using the gates, writing the code in gate level. So every time writing in the gate level is not an easy task, and it will be very difficult for us to write everything in gate level. So sometimes there should be a trade-off between these two. If you do completely behavioral, then the code will do the mapping to the gates. If you do the structural, then the code will the simulator will easily understand. If you completely do this, it becomes very difficult. It is difficult for us. And if we do completely behavioral, then we cannot be sure how the simulator is understanding and how it is implementing. It will work, but here it might not be optimized, I can say. So we are not optimizing it, right? So it depends upon the simulator. So it is not optimized. The simulator might or might not optimize the number of circuitry that is needed to implement this. But it is again a trade-off. As far as we can go structural, we can go structural. But if it is difficult and if it is becoming much complex, then we will do behavioral. So there is a trade-off between these two. So it is again up to you. If you are fine with the cost, this would be very easy. So I can say this is easy to write. So this will be very easy to write, but it is not optimized. It is difficult, but optimized. So these are different modeling that we can keep. So when we write it gate level, then we call it structural code. If not, then it is behavioral code. So both will implement the same logic, but the amount of number of gates, the cost of the circuit, here it is optimized, here it is not optimized. Here the simulator is doing the job. So we might not know whether it is optimized or not, and majority of the cases it might not be optimized. Coming to the description styles. So there are different description styles. So we are describing some circuit. There are different description styles. One is the data flow, which is continuous assignment. So here we'll use assign.
Sir?
So yes.
In the last slide, optimize, you mean we are using the less number of gates in the FPGA?
Yes,
Is that what you mean?
optimized in the sense of hardware. How many gates or how many gates are needed to implement that logic?
Okay.
Here we are telling the Verilog code which gates to be used where and how many. So here we are fixing it. We are optimizing it by ourselves and we are fixing it.
Yes.
Whereas here we are giving it the algorithm level of logic, and the simulator is deciding how many hardware is needed. So there are two description styles. One is the data flow, where we'll use SN. So whenever we are using SN, it comes under data flow description style. So again, it is continuous assignment. As you remember, continuous assignment means which data type? Wire.
Wire.
Yes.
Wire,
so
wire.
only wire can be used SN. You cannot use ridge for SN. It cannot be used because this is continuous assignment. So C will be continuously changed whenever A and B are changing. C will not hold a value which comes under a wire data type. So for this data type, you cannot use. Now coming to the other description style, which is behavioral. So here we call it continuous assignment. Here we are calling it procedural assignment. Again, procedural assignment has two types of assigning. So one is blocking, other one is non-blocking. So here we will write A equal to B. Here we will not write assign A equal to B. Directly we will write A equal to B or A less than or equal to B. So what is the difference between less than, equal to and equal to, that will come. But as it is holding the value, this is used for rich data type and it will hold the value. So both can be used, but what is the difference between these two, that I'll explain in the upcoming slide. So this is used for wire data type. This is used for reg data type, and you cannot interchange. For reg, you cannot write SN, it will throw an error. And for wire, you cannot write A equal to B, again, it will throw an error. So if you are defining wire, then you should use continuous assignment. If you have defined it as reg, then you have to do the procedural assignment. So whenever there is a reg, it will be event trigger. So there has to be some event that triggers, and at that point it will change the value and it will hold the value until the other event comes. So before we go into blocking and non-blocking statement, so equal to means blocking, less than or equal to means non-blocking. So in before we go into that, so there is something called initial as well as always loop. So initial loop means it will execute only once. Always means it will execute forever. Again, initial can only be done in simulation. It cannot be done in hardware. So this is only for simulation purpose. Always it can be done in simulation as well as hardware. So last time, if you have remembered, I have done LED blinking, right? So it is a forever loop that I have loaded into the FPGA. So where I have used this always. So I have used this always. So it will keep on running until I turn off the supply to the FPGA. It will keep on running and it is a forever loop. So last week when I have shown the LED, I have done this forever loop and it will keep on going. So blocking statement. So in the blocking statement, we are using equal to. In the non-blocking statement, we are using less than or equal. So either you can use this procedural statement under initial or under always. So initial means it will execute only once, and again it is simulation. When we are dumping into hardware, it does not make any sense. So initial is only for simulation. When we are implementing hardware, you should not use initial, you should use always. But this is for simulation purpose. So that's what we are saying. Blocking statement means it will be executed sequentially. And non-blocking statements means it will be done parallelly. So if I write a equal to, then first this line will be done, then next this line will be done. So at t equals to 0, at t equal to 0, we have a equal to 1, b equal to 2, c equal to 0. After 10 seconds, t equal to 10 seconds, we have a equal to b plus c. So a equal to 2, b equal to 2, c equal to 0. Now at t equal to, after 10 seconds is over. Now I have done this. Now again I am waiting additional 20 seconds. So at t equal to 10 plus 20, 30. I have a equal to same, b equal to 2, and c is equals to 3. If you come over here at t equals to 0, maybe I'll change the color. At t equals to 0, we have a equal to 1, b equal to 2, c equals to 0. So both will be doing parallelly. So if I, but this will happen at t equal to 10, this will happen at t equal to 20, because both are going on parallelly. So at t equal to 10, I have a is equal to b plus c, 2, b is equal to same, 2, c is equals to 0. And at t equal to 20, I have c equal to a plus b. So a is same and b is 2 and c is a plus b. So c should be 4. But what happens is, when you write less than or equal to, it will take the value that is available at that instant. So that hash 20 is coming later, but less than or equal to is coming. So whatever value that is available before, it will take that value. So a equal to 1 as well as b equal to 2. So c will take 3. Understood. So as this is happening parallelly, it will not take the value of a, that is the updated value. It will take the value that is available at that instant. So whenever this is happening, or for your ease, I'll tell you. Say this
Sir,
hashtag is
please
not
repeat
there.
these once.
Yes.
I am
Okay.
not clear.
Okay. So assume these are not
Please,
there.
these two, sir.
Yeah. So
These two.
yeah, I'll explain. First of all, assume that this is not there, this is not there. Now what happens? A is b plus c, right? So a is, so both will happen at a time. Both will happen at a time. So first a will be updated, also c will be updated. So a is being updated with these values of b and c, which is 2 and 0. A will be 2. B is not updated, b is 2. And c is also updating at the same time. So while c is being updated, a has not updated. So c will take the previous value of a, not the updated value, because those two are being updated at the same time. So a will take the present value of b and c. C will also take the present value of a and b, which is 1 and 2. So c is 3. This part, is it clear? So when we are writing,
Yes, sir, it is clear.
as these two are occurring parallelly, if it is sequentially, say this is not there and also this is not there. So first this line will be executed and then the execution of this line will start. So A will become 2, and as A value has updated, now C will take the updated value of A and C will become 4. Whereas here both are executing parallelly. If this and this are happening parallelly, when C is executing, what is the value of A? A is this value, because this has not happened yet. So they're happening parallelly. But when we put this #10, so what happens is this value will be reflected after t equal to 10. So whatever A value is there, so it will be reflected after t equal to 10. And this is #20, which means this C value will be reflected after 20. Understood. So first, forget about the time. First, you calculate these values. Now these values will be updated after #10 as well as #20. So in non-blocking statement, just to summarize, all the, say if A is less than or equal to B plus C, B is less than or equal to C plus A, C is less than or equal to A plus B. So A will be what? B plus C, which is 2. And B will be what? C plus A, which is 1. And C is what? A plus B, which is 3. So it will, all of them will happen at the same time. So they will not take the updated values of ABC. They will take the values that are available before. So all these values will take this A, B, C values. Whereas here they are occurring sequentially. So the values are updated and it is taking the updated values. I hope this part is clear.
Yes, sir. Sir, it is clear. Sir, REG 320 A comma B comma C. Does it means like A is 4 bits, B is 4 bits, C is 4 bits?
Yes. So thanks
If
for
I
asking.
want, sir,
Mhm.
B and C are just bits, single bit, and
Yes.
only A is 4 bits, then how
Yes,
to represent it?
yes. Yeah, before coming to your query, so as you see here, it is procedure assignment reg. So whatever I'm using for this procedural assignment, I am naming it as reg. Say as he has asked, let me go back here. So how do I define, say, reg? So if one or more than one variable are in the same family, you can put a comma and you can define them in the same line. Say reg 320 A and say semicolon. Now B and C are single bit. So I have to write reg B comma C semicolon. So until and unless you specify the size, it will be single bit. If it is a vector, then you have to name it vector. By default, it is scalar. So by default, wire or reg, it is scalar. Similarly, if I want to define wire, say B is 5 bit, wire 420, B is 5 bit. Say A is 3 bit, wire 220, A. C is single bit, wire C. I cannot write these in the same line because this is of 5 bit, this is of 3 bit, this is of single bit. I hope it is clear.
Yes, sir, clear.
Okay. So we'll move on to our next topic, which is event control. So as I have told, the register should be triggered by some event. Either it is a regular event or it is event or control. We'll come to that point. Say there is a D flip-flop.
Sir, one query.
Yeah.
Like you have mentioned procedure like blocking you said.
Mhm.
In the other case, you have C equal to A plus B, then how to define them?
Here also it is same. Here I am defining wires. Here I am defining reg. And here I will use Sn C equal to A plus B. So here Sn is the word. Here I will not use Sn. I will directly use A equal to B or A less than or equal to B.
Okay, sir, if I want to like A less, I want to check A less than or equal to B, I have to check in the
If-
continuous assignment.
If A is less than or equal to B.
Okay.
And did you install
Okay,
Xilinx
sir.
ISim software?
Sir, I tried installing, but it is taking too long time.
It might
I
take,
don't know what's the problem with
it might take extra time depending upon your laptop processing speed. So like in the video, I think he has also shown sometime. Maybe you just try waiting it for some time.
Okay, sir. Okay, sure.
So as I have mentioned, this should be event triggered. So that event will be either regular control or event plus control. Coming to that point, say there is a D flip flop and it has a clock and it also has a reset. This is clock and the input is D, output is Q. So the code is as follows: D flip flop, that is the name. It has QD clock reset ports, D clock reset are inputs. So by default it is single bit. Output by default it will be wire. If it is reg, then you have to mention it reg. If it is wire, you can write output Q. So I have written always at the rate pos edge clock begin. So if there are more than one lines, you have to write in begin and end. So if there are more than one lines inside always, you have to write begin and end. So multiple lines should be written in begin and end. So here it is single line, so we don't need begin and end. So what is happening is, Q will be 1 if D is equals to 1, else, or like Q is equals to D at rising edge of clock. So at positive edge of clock, I will check if reset is there. Again, if reset is there, then Q is 0, right? Q equal to D at this and Q equal to 0 if reset. Now, how this reset is happening? Reset is synchronized with the D flip flop. So whenever there is a positive edge at the clock, then only we are checking whether the reset is 1 or 0. If reset, then we are giving Q 0, else we are passing D to Q. So this is synchronous because the reset is synchronized with the clock. If it is asynchronous, so irrespective of the clock rising edge, if I click reset, I want it to be reset. So in that case, what we will do? So in this case, we'll do pause edge clock or pause edge reset. So whenever there is a pause edge in the clock or whenever there is a pause edge in the reset. So whenever there is a pause edge in the clock, whenever there is a pause edge in the reset. So if I have clicked reset, it has gone from 0 to 1. So the code will detect this rising edge and it will reset. So it is not synchronized with the clock. So the reset is not happening in synchronism with the clock. It is happening in an asynchronous fashion. So whenever I'm clicking reset, whether the clock is 0 or 1, irrespective of that, my reset is happening. Understood?
Sir, you are saying if it is one line, we don't need this.
Begin
What
and
is that point? Please
begin
repeat.
and end. So say within always, some
Sir,
always
please
enter.
repeat this regular event and event or control once again, please.
Okay. Regular event means there is only one event, which is the clock. And event or control means we have more than one event, which is clock or reset in the case of D flip flop. And here the resetting is not happening in synchronism with the clock. Here the resetting is happening in synchronism with the clock because the reset will happen whenever there is a rising edge in the clock. So that's why it is synchronous. And here, irrespective of the clock rising edge, the reset will happen. That's why it is asynchronous. Say I have,
Okay, like
if A is equal to B, I say C is less than or equal to A, B is less than or equal to C. There are more than two lines, so I have to write begin as well as end. So if there are more than two lines, I need to write this. Here I have single line, so begin and end is not necessary. Even if you write, it is not an issue.
okay.
So this one point is the LSB. This is the present
So
value of
this, yes. So again, that's a good question. Whoever has asked me. Let me change the color. And we will come to red color. So if I say 1 dash B0 means it is 1 bit. And this should separate binary. So 1 bit binary. So it can be either 0 or 1. Say I'll write 4 dash B. It means 4 bit binary. So I have to specify 4 bits. 0, 0, 1, 1. I can write 4 bit decimal and the decimal value is 10. So this 10 can be like can be implemented using 4 bits. So in decimal, I'll write 4-bit
Sir?
decimal 2.
Sir, for 4-bit decimal, you are representing 10-0 means I guess we need 8 bits, right?
Why do you need
You are
8
saying
bits for 10?
4-bit in the sense for 1, it will, decimal means in the sense 0 to 9 it will be.
No, decimal can be more
10.
than 10 also, 11, 12, 13. See, 4-bit means from what value to what value you can go. 0 to
0002
4-bit, not decimal.
4 zeros.
4-bit.
0 to F.
Yes.
Sir,
Mhm.
sir, in this, you are saying, so if in the first case, we are making the output reset at the positive edge clock. In the second case, irrespective of positive edge of the clock, we are making output to be 0.
Yes.
Sir, here in this else, or this q less than the q is made to be D.
Yes.
Uh,
So for every case, we should check. The reset has the highest priority, right? If reset is clicked, Q should be 0. So first I am checking reset. If reset is there, then I am making Q 0. If reset is not there, then only I will pass Q.
Sir, I want to, I'm trying to understand the difference between this q equal to D and then q less than D.
So again, you can still use less than or equal to, because equal to is non-blocking and less than or equal to is non-blocking. Here, there are no multiple sequences, so you can still use less than or equal to and it will work fine. So there is no issue.
Yeah, here there is no the time we are not any specifying here.
Yes, because if there are
Like-
more than one sequence, like more than one operation, like C less than or equal to A, B is less than or equal to C, then B will take the previous value, not A. But if you write C equal to A, B equal to A, B equal to C, then B will take C. B will take A value. So C is updated with A, B will take the updated value of C. But here there is no such thing. So less than or equal to will be the same thing. So these are the events. Now, so till this point, we have discussed about Verilog. So to summarize, we have discussed about Verilog. So introduction to Verilog. So I can say introduction, and then we have discussed different data types. What are different data types, where they are going to be used, and then different modeling, structural or behavioral modeling, then description styles. And then we have discussed also expressions and operators. So expressions and operators. And then we have seen different procedural statement. One is non-blocking versus blocking. So like this is a summary of the Verilog that we are going to use in this semester. So and this is enough, sufficient for this course. And in the end, we have discussed event-based asynchronous or synchronous. So different types of events. Now, using whatever we have learned till now, we'll implement ripple carry adder. So, which is we are considering a 4-bit ripple carry adder. So first we'll understand the Verilog HDL, then we'll go into the Xilinx simulation and see whether our code is working or not, or how to use Xilinx ISim. So as you know, 4-bit triple carry adder means we have two inputs. So this is input 1, and this is the input 2, and it also has a carry. And output is again 4-bit. 4-bit output with the output carry. So how do I implement a 4-bit adder? I can use 4 1-bit full adders. So that's what we are doing. So this is the LSB. This is the MSB. So C in A0, B0. So A3, A2, A1, A0. This is MSB. This is LSB. B3, B2, B1, B0. This is LSB, this is MSB. So first we are starting with LSBs as it should be. So A0, B0, C, output S0, carry C1, which is the input carry to the next full adder. A1, B1, C1. Output is S1, C2 is the carry, output carry, which will be the input carry to the full adder. A2, B2, C2. Output is S2, sum, and carry is C3, which will be the input carry to the other full adder. So A3, B3, C3 inputs. Output is S3, C out. So this is again LSB, and this is again MSB. So we are implementing a full ripple carry adder, 4-bit adder using 4 full adders. Now full adder means input is A0, B0 carry, output is some carry. So this will implement using half adders that will come. So I am adding this A3, B3, A1, 0, B3, B2, B1, B0, and C. So if I do the summation, so what I am getting, summation is S0 with a carry C1. This summation is S1 with a carry C2. This summation is S2 with a carry C3. This summation is S3 with a carry C out. So this is how my logic works. Just like any other addition, binary or decimal, that's how we do. So the same thing, but here it is binary. So each is a single bit binary. Overall it is 4-bit. Now this individual implementation has to be full adder, which can be implemented using 2 half adders. So we'll come to that point. So 4-bit adder implementation using full adder.
Here we'll make initially Cin to be 0, right?
Initial, no, it cannot be like whatever Cin is there, that should be there. Like the user is giving the Cin, right? It can or cannot be 0. I mean, may or may not be 0. So the ripple carry adder is as follows. So I have defined the input. So here I will define the input, output, everything. So it has 4 such full adders. So I'm defining accordingly. So this is my output sum, output carry, input A input, B input, carry input. Similarly for adder 2, output sum is S1, output carry is C2, input is A1, input is B1, input carry is C1. Similarly, say this is full adder 1, full adder 2, full adder 3, full adder 4. Here the output is S2, C3, input is A2, B2, C2. That is what I'm writing here. And for the final adder, let me change the color. So output is S3, C out, input is A3, B3, and here C3. So that's how I'm defining full adder. Now again, I have to define full adder. So the module name is full adder, which is common for everyone, but I'm naming it differently, FA1, FA2, FA3, FA4. Now I have to see whatever I have done in the previous, I'll show. So we are doing the sum, right? S0 with carry, C1, S1, C2, S2, C3, S3, C0. So, so this is which full adder, FA1 or FA2 or FA3 or FA4? Can you tell me?
FA1.
FA1. So this is FA1, and this one?
FA2.
And this one? And
3.
this one, FA4. So that's how I have defined. Now I'll define full adder using 2 half adders. So this is a full adder with A input, B input, C input, output to be sum as well as carry using 2 half adders. So for the full adder is this. So input is S, C, A, B, C. So it can be defined using 2 half adders. For the first half adder, output is say S1 and carry is say C1. Input is A, input is B, and input is so only 2 inputs, A and B. For the second half adder, input is S1 as well as C. So input is S1 as well as C, and the output is sum, and the other output is say C2. Now carry is what? C1 and C2. So carry is equal to C1 and C2. So here there will be another line which says C is equal to C1 and C2. So we are rearranging using 2 half adders, which is the logic everyone as you might know, implementing full adder using half adder. Now I have 2 half adders, and the half adder logic is this. So half adder has 2 input, 2 output. A and B, sum is XOR and carry is AND. So half adder has 2 input, 2 output. I'm representing XOR gate with S as output, A and B input, and AND gate with C as output, A and B as input. So this is the top-down approach, as you can see, top-down approach. So we have started with ripple carry adder. So we have started with ripple carry adder, and in the ripple carry adder, we have put full adder, and in full adder, we have used half adders, and then in the half adders, we have nothing but gates. So this implementation is pure gates, and using this we are developing the higher hierarchy model. So we are coming from top down. So this is again top down approach. So until this point, I think it is a very common topic that you had learned in your digital circuits. If this part is clear, we can go into the simulation part. I hope it is clear till this point.
Sir,
Yeah.
just the variable, so we are calling half adder, and how the variables S, C, A, and B is matched here, sir? Is mapped here.
Yeah. So there are two methods of connecting the ports. One is the ordered list. Maybe I'll change the color. One is yellow will be very. So one is the ordered list, and the other one is binary. So I have told in the ordered list you have to use the same sequence. So I have used the same sequence. S1 is S, C1 is C, A is A, B is B. Here S is S, C2 is C, S1 is A, C is B. So sequence should be same. Here we will define which port is connected to which port. So there is no
since here we are given in the sequence, so no problem.
Yes. Otherwise you have to give like this dot S of S1, comma, dot C of C1, comma, dot A of A. Comma, dot
that we said previously, sir.
Yeah. So I suggest you everyone to write the code in ordered list and then write the code in name. You will make mistakes, and in coding we will learn by making mistakes. So the main part is correcting your mistakes rather than not making mistakes. So if you make mistakes and if you correct it, then you will learn better than not making mistakes at all. So we should also learn how to debug our own code. So you might be facing some issue. It might show an error is there in this line. Then you will see and you have to understand what error. It will not say what error is there. It will say sometimes there is an error. So you have to understand. So it will make you understand Verilog code in a better way, and you will be able to understand and code better. So if this point is clear, then I can go to the simulation point and I can show. I hope it is clear this point, right?
Sir, actually the second half adder C2 is nothing but the C of full adder, right?
Okay, I'm coming.
No, sir. No, just I'm asking.
Yeah, so actually the output carry is carry of first half adder and carry of second adder. So output C is C1 and C2. Sorry, or okay. So okay, you are correcting, right? Oh, thanks. This is or. So this is and. Thanks for correcting. This is and. This is and. This is or. So the carry is or of C1 and C2. So this is C1. So this is C1 and C2, and this is C1 or C2. This is not one. This is the vertical line. Okay. Yeah. Thanks for correcting. We'll go to the simulation. So first ripple carry adder. I'll quickly show. I hope you all have installed the software and started doing the simulation, which is actually mandatory. Understanding the Verilog is easy compared to writing the Verilog code. It is same with any language. So this is my ripple carry adder. So if you see, I have S, C out, A, B, C in. Input is A, B, which is a vector. Is this visible? Maybe I'll increase. And,
yes, sir.
Yes, sir, visible.
Yeah. So this is my AB, which is again a vector because 3 0. C in output is also a vector, so 3 0. And C out is 1 bit. If you have not specified, by default it is 1 bit. And I have used wire C1, C2, C3 because it is continuously driven, right? It should continuously change. There is no event based or procedural thing. So wire C1, C2, C3, and this again is exactly same what we have discussed. So this is the FA1 for LSB. This is the bit next to LSB. This is the bit next to it, and this is MSB. So this is LSB, and this is MSB. So let me clear all my drawings. So this is about the ripple carrier adder. So if you see, again, there is a less than a minute. So if this meeting ends, kindly join. So as you can see, there is a plus sign. If you click on the plus sign, there are 4 such full adders which will describe this. So let me click on any full adder. So my full adder code, I have put S, C out, A, B, C in. Now these are all single bit. Now all of them are single bit. All of them are 1 bit because full adder is of 1 bit. So 1 bit inputs, 2 inputs and a carry, 1 bit output and 1 bit output carry. And I have put a wire S1, C out and C out. So why do I need wires? Because this is one wire, this is another wire, this is another wire. So S1, C1, C2. So that is what S1, C out 1, C out 2, and 2 half adders. I am using another OR gate. That's why I was using another OR gate, which is again a wire. And C out is C out 1 plus C out 2. So I'm using an OR gate. So again, you can see a plus sign because full adder is what? Made of half adder. Let me enter half adder. So half adder, it has 2 inputs, not 3 inputs, unlike full adder. So it has 2 inputs, 1 bit again, A comma B, and the output is S comma C out. So I am using one XOR gate for sum. So this is for sum, and AND gate for carry. So if I'm let me clear all my drawings. So this is the simulation part, this is the implementation part. So if you want to implement this in the hardware, then you have to first synthesize, then implement design. So I have already synthesized. So there is this plus sign. If you click, you can view the RTL schematic. Click on view RTL schematic and then click OK. So it will give you the what you can say the hardware modular level of how this is being implemented. So this is the actual original RCA. So this is RCA. Double click on this and you can zoom out. So you can see one full adder. So there are 4 such full adders, but it is showing one as it is directly mapping. So it is being overlapped. So full adder has A. If you see A30 is a vector, but it has mapped. So there are other full adders below it. So its input are A, B, C in, output is C out S. So ripple carry adder has a full adder inside. Click it. I'm clicking this and it has a half adder, another half adder. So the first half adder, I think we can map. So first half adder output is input to second half adder and carry is the input to second half adder. So first half adder output sum is the input to other half adder and carry in is the input to the other half adder. Now carry out of the first and as well as second, or of those two is the final carry. So or of these two carries, this carry is the final carry. So this is our one full adder which has 2 half adders as well as 1 OR gate. Now I'll double click on the half adder to see what is inside. So they have this AND operation. So they have this inverter as well as NAND. So there, I think these are buffers. So one AND operation and one XOR operation. So they have the block might not be exactly what we draw. So this is how they are representing XOR. So the sum is XOR and AND is carry. So if I want to go outside, you click. So if you click, it will change into blue color. So now this is selected. Click on half adder. It is selected. Right click and hide block contents. Again, half adder is selected. Click on full adder. Right click, hide block contents. again click on RCA, right click, hide block contents. So this is the hierarchy. So we have gone from RCA to full adder to half adder, two half adders plus one OR gate, and then inside half adder we have seen one XOR gate and one AND gate. So let me close this. So this is the implementation. We are in the implementation. If you want to do simulation, you have to select which one you want to simulate, any single full adder or triple carry adder. I want to simulate triple carry adder. Click on triple carry adder. Here right click and rerun all. So let it happen. So it will simulate and it will open this ISim. Now where is this ISim? Can you see this ISim? Hello?
Yes, sir.
Okay. So in this ISim, you have to give the input. So right click, force constant, say A, I want to give a 4-bit binary, right? Say 0010 I'm giving. Okay. And B, you tell me one input, 4-bit.
01110.
0110. Okay. And carry in either it is again scalar, right? Either it can be 0 or 1. So let me give force constant. So it can be 0 or 1. What do you want?
0, sir.
0. Okay. I'll click and here I have to specify time 1 microsecond. Let it be, and I have to click this button. It will run for specified amount of time. So this is to maximize or minimize. So let me zoom in till this part. So 0010, 0, 110. If I add, we'll get 0 plus 0, 0, 1 plus 1, 0 with the carry 1, and again 1 plus 1, 0 with the carry 1. So this is my S and this is my C. So you can use this and see. So this value is 0 here, and this value is 1000. So this is working, right? You understood? These values are correct, right? So this is working fine. So I can do in a different way. So let me do it in a somewhat different way. So I'll make this force constant with the value 1, 1, 1, 0. So 1110. And this I'll make force constant 0001. So now the summation is 1111. Now I'll give a carry if clock, which will vary from 1 and 0. I'll give its time period may 1 microsecond time period I'm giving. So I'm applying, and now I'm increasing the time period to 0. So let me see what will happen. Now I'm simulating it, I'm minimizing it. So as you can see, let me zoom into this part. So okay. So 1110, 0001. So the sum is 1111, right? So if the carry is 1, then the sum will be 0 and C out will be 1. But if the carry is 0, sum will be 1111 and output will be 0. So my carry decides. So I have put the values in such a way, if the carry is 1, my sum will be 0, carry is 1. If my carry is 0, sum will be 1111, carry is 0. So this is how you can play with this. So you can give multiple inputs and check. So you have understood this part, right?
Sir?
Hello. Yeah.
For changing it is taking some value. It is taking some time.
Yes. So it is. So after 1 second, the simulation is starting.
No, sir. While we are switching between that is C we are switching.
Yeah.
C we are ranging between 0 and 1. So at that time the output is toggling between 0, 0 and 1, 1, 1. So that change does not happen instantaneously, it seems.
Why?
But sir, because there seems to be some ramp here.
No, this is not ramp. Like that's how they represent data. So that's how they represent data. So let me maximize it. So like it is just the representation. So in digital, if a value is changing, they'll use this kind of symbol. You may find in any data sheet also. So that is just a representation. So whenever they change data, they'll use this sign. It does not mean that it is taking this much time. No, it doesn't. That is just a representation. That's it. Understood?
Yes.
Okay, so I hope this part is clear. So you can play with this. You can give different input output. So this is the ISim simulator. You have to give right click and either you can give force constant clock. So this you will get to know once you start coding. So keep that in mind and do different coding. So you can do only half adder or one full adder or ripple carry adder. So you can try out different codings. Now we'll go into binary numbers. So binary numbers you might have studied in your C. There are three ways of representing a binary number, which is straight binary. Another one is 2's complement, and the other one is offset binary. So in okay, so let us go into the details. So binary numbers are three types. One is straight binary, and the 2's complement, offset binary. So this is unsigned. So it means it can go positive numbers, 0 to say some 2 to the power n minus 1 also. So it is unipolar, only one side. These two are signed. So it is bipolar, say minus some x value to positive y value. So this can represent bipolar voltages, and this is signed. This is unsigned and it can only represent unipolar voltages. So now coming to this. So I have considered what? I have considered a 3-bit number. So 3-bit number B2, B1, B0. So there are 8 such possibilities. So 1, 2, 3, 4, 5, 6, 7, 8. So you must know if it is 0, 0, 0, in straight binary it is 0. And it is going 1, 2, 3, 4, 5, 6, 7. Maximum is 1. When all bits are 1, it is 2 square, 4 plus 2 to the power 1. 6 plus 2 to the power 0, 7. So maximum value is 7. Whereas in the case of 2's complement, how do? We do 0 into 2 to the power. So we will do B2 into minus 1 into 2 to the power 2.
Power of n minus 1 minus 1.
Yeah, 2 to the power 1. Sorry.
2 to the power of n minus 1 and then minus 1.
So here n is 3. So n minus 1 is 2. So we will get 2. So if I check the first 0, 0, 0, it will be 0, 1, 2, 3. Until this bit becomes 1, there is no issue. When this bit becomes 1 and it is 1, 0, 0, we will have minus 1 into B2 is 1 into 2 square plus 0 plus 0, which is minus 4. So this is the maximum negative voltage that we can go, and then it will keep on decreasing, minus 4, minus 3, minus 2, minus 3. In the case of offset binary, we have to toggle the first bit. So from offset binary to 2's complement, we have to invert the first bit. So invert first bit. So if this 0, 0, 0 is in offset binary, 0, 0, 0 is in offset binary, it means in 2's complement it is 1, 0, 0. So in 2's complement 1, 0, 0 means minus 4. So minus 4. And 0, 0, 1. So 0, 0, 1. So this is offset binary. And this is 2's complement. So in offset binary, 2001 means 2's complement 101. In 2's complement 101 is minus 3. So minus 3. So similarly, you can get the other values also. This is like very, very simple as you know. So you can get the other values. So minus 4 is mapped here. Minus 3 is mapped here. Minus 2 is mapped here. Minus 1 is mapped here. And again 0 is mapped here, 1 is mapped here, 2 is mapped here, and 3 is mapped here. As you can see, both are signed, and this is unsigned. Yeah.
Sir, actually, in this 2's complement, sir, when this becomes 1, when B2 is 1 and B1 and B1 and B0 are 0, then at that time it should be a minus 1, no, sir.
by B2 into -1 into 2 square, right?
Okay.
So it is like this: -1 into Bn into 2 to the power, say Bn minus 1, 2 to the power n minus 1, plus Bn minus 2 into 2 to the power n minus 2, plus up to so on, B1 2 to the power 1, B0 2 to the power 0. Sorry, this should be B0. So here we have what? 1. So -1 into Bn minus 1, which is 1, into 2 to the power n minus 1. Here n is equal to 3. For our case, n is equals to 3. So into 2 square plus 0 plus 0, which will give -4. I hope it is clear.
Yes, sir.
Okay. So now we are going to the quantized voltage. Say, for example, consider a 10-bit ADC and Vmin into Vmax. So for 10-bit, it will start from 2 to the power 9. And by this, you can say it is a straight binary. There is no sign. So straight binary. Straight binary NX is the output, Vm into Vmax. So we define input span as V maximum minus V minimum. Say the input is 0 volt to 1 volt. Then span is 1 volt. If the input is -1 to 1 volt, then the span is 2 volts. So that's how span is defined. And the resolution is V span by 2 to the power n. So here it is 10-bit. So V span by 2 to the power 10. So resolution of ADC, how do we define? It's input span by 2 to the power n bit of the ADC. So if you have to generalize, it will be V span by 2 to the power n. So this is the resolution. So if you want to find the quantized value of the output, then it will be nx into V span by 2 to the power 10. So let me give an example here. So we'll consider Vmax. So let me change the color. We'll take one example quickly. So say Vmin is equal to 0. Vmax is equals to 1 volt. So from this I will get V span is equals to 1 volt. And it is 10 bit. So 2 to the power n is 2 to the power 10. Say our ADC output is 512. Now I have to know 512 means what is the voltage? How much voltage 512 actually mean? How would I know? I will substitute this in this formula. So I will get Q of VA is 512 into V span is 1 by 2 to the power 10. So it will be 0.5. So I know that if my output of ADC, which is a digital number, if it is 512, actually it means the input to it is 0.5 volts. And what is the maximum value of NX? Maximum value of NX is, say NX for 10-bit, it can vary from 0 to 1023. So NX is NX maximum, you can say. NX maximum is 1023 times 1 by 2 to the power 10, which will be close to 1, but 0.99 voltage. So you cannot reach the maximum input voltage, but it will be close. So if you increase n, then that so here resolution will increase, which means error voltage will decrease if n increases. So if you increase the number of bit, then the error will be, or the jumps in the discrete value. So ADC is a discrete, right? So it will take discrete value. So this jump will decrease if the number of bits increase, but again cost will increase. So this trade-off will always be there. So this is the quantized voltage.
Sir, here if you put 2 power 10, then 1023 is the right thing, right? Here, just for example, we put 512, right?
So like I'm saying, say NX is 512. Like NX can be 0 to 1023, any value, right?
Oh, this is intermediate way.
We are taking any value in between. Say NX is 512. I'm checking 512 represents what voltage. So I'll put this here and I say 512 means the voltage is 0.5. So this is the real voltage, 2 hour volt. And this NX is 512 to the FPGA volt. So this is the digital number. This is the quantized voltage, analog voltage. So I'm checking. So NX minimum will be how much? NX minimum will be 0 into 1 by 2 to the power 10. So the sorry, not NX minimum. So this should be Q of VA max, and this also Q of VA minimum. So Q of VA will change from 0 to 1023 by 2 to the power 10 in the steps of 1 by 2 to the power 10. So there are 1024 steps starting from 0 to 1023 by 2 to the power 10, and each step increment is 1 by 2 to the power 10. So we are just mapping the digital number with the quantized voltage. That's it. This part is clear, right? Like this is just simple. We are just mapping. Okay. Here comes the actual main, what can I say, the building block for the upcoming week. So the fixed point arithmetic or concept of Q format, I'm stressing this Q format is very much important. So whatever will be doing in the upcoming weeks, voltage mode control, current mode control, anything, we use something called Q format. The understanding of this concept is very much crucial for understanding the upcoming modulation techniques implementation in FPGA. So this Q format is very crucial. You should spend some significant of time on this, solving few problems, understanding this. So I don't know if it is available anywhere. It might not be. So SARS lectures are your reference. You go through the Q format multiple times. I'll also quickly describe. So assume there are 4-bit numbers. What is its NX decimal value? 2 cube into B3, 2 into 2 square, 2 to the power 1 into B1, and 2 to the power 0 into B0. This is 4 bits, so n minus 1. Now, what if I take 2 square common and represent this? So I am calling this ny decimal. So I am calling this ny decimal. And I am calling this n scale. So this is, I'm just taking common n square. So I'll come to this point and why are we doing this? So for example, last time we have considered 10-bit ADC, but for the simplicity of understanding or ease of understanding, we are considering 4-bit ADC. So from the previous slide, we have understood Q of VA is nx decimal into V span by 2 to the power n. Say I have given 2-volt input span.
Sir,
with 4-bit, yeah.
the last one beside B0 should be 2 to the power minus 2, right?
This one.
Beside B0.
Beside V0. B0.
B0.
Oh, okay. Thank you. Yeah. Thanks for correcting. This is 2 to the power minus 2. Okay. So I have written nx in terms of some ny into n scale, where n scale is 2 square. So here Q of VA is nx decimal into V span by 2 to the power n. So V span by 2 to the power n. So V span is how much I have given? 2 volt. And 2 to the power n is what? 2 to the power 4. So 2 to the power minus 3. So Q of VA is nx decimal into 2 to the power minus 3. So it is similar to like this, right? Say nx decimal is ny into say some 2 to the power n. So if I bring ny decimal here, I'll get nx decimal into 2 to the power n. So this is what we are getting. So I have represented in this way. So now this becomes 1 by n scale or n scale. You can consider the new n scale to be 2 to the power minus 3. So if it is 2 to the power minus 3 into
minus n.
But here it is say minus 3. Again, it depends upon V span and 2 to the power n. So nx decimal is this.
This nx decimal into 2 to the power minus n, right?
No, V span is 2, right? So it will be 2 to the power 1 minus n. That is 2 to the power 1 minus 4, which is 2 to the power minus 3. Understood? V span by 2 to the power n. V span I have given 2 volts and 4 bit. Okay. Say if V span is 1, then it's 2 to the power minus n. It depends upon V input span. So that's why like we cannot generalize. So basic factor is V span by 2 to the power n. For this example, only for this example, it is 2 to the power minus 3. From here, we know nx decimal. So let me change the color to some maybe blue. So you have to substitute this nx decimal in this equation. My Q of VA is nx decimal into 2 to the power minus 3. Right. So nx decimal is this. So if I take 2 cube common, it will be this. But if I multiply by nx decimal into 2 to the power minus 3 means, so this will get cancelled. So my ny decimal is this. So my ny decimal is this. Understood how I am getting ny decimal? I am multiplying nx decimal by 2 to the power minus 3, which is giving me ny decimal. Understood?
Sir.
So now the final expression of ny decimal is 2 to the power 0 into b3 plus 2 to the power minus 1 into b2 and 2 to the power minus 2 into b1 plus 2 to the power minus 3 into b0. So I can represent this as b3 dot b2 b1 b0 as if there is a virtual dot, and say this is 2 to the power 0 coefficient, 2 to the power minus 1 coefficient, 2 to the power minus 2 coefficient, 2 to the power minus 3 coefficient. So if there is a dot here, if I want to get the ny decimal, I can directly say b3 into 2 to the power 0 plus b1 into 2 to the power minus 1 plus b1 into 2 to the power minus 2 plus b0 into 2 to the power minus 3. So I am keeping this virtual dot for my ease. So this I would say virtual dot. So this virtual dot is for my ease to understand, so that using this b3, b2, b1, 0, I can directly convert it to ny decimal. So then we write the Q format with number of digits that are there before dot, number of digits that are there after the dot. So Q1.3 says that it is a 4-bit number. It is a 4-bit number with 1 bit before dot and 1 bit after 3 bits after the dot. Is that clear until this point?
Yeah.
Now we'll go into the concept of Q format. So as I have told, it has a virtual dot with n integer bits. If it is n dot m, n integer bits, so we call this integer bits. Why? Because the power will be 2 to the power 0, 2 to the power 1, 2 to the power 2. Fraction bit, it will be 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. Say for example, we have n, say Q2.3. So how many integer bits are there? How many fractional bits are there? 2 integer bits and 3 fractional bits. So it is total 5-bit number with 2 integer bits and 3 fractional bits. Say if it is straight binary, then it will be plus. Sorry, this is plus 2 to the power 1. So if it is 2's complement, we have minus over here. So these two are integer bits and these two are fractional bits. So I am keeping this virtual dot for my ease. Now say nx is 11010. I have a dot here. So what will be its value Q of VA? What is the Q of VA? I have to map this, right? So this say this is B2,
3 point
B1, B0, say B minus 1, B minus 2, B minus 3. I represent this. So my value will be minus 1 into B1 into 2 to the power minus 1 plus B0 into 2 to the power 0 plus B1 into 2 to the power minus 1, B2 into 2 to the power minus 2 plus B3 into 2 to the power minus 3. So this is my B1.
plus 1, sir. First one is
Yeah.
plus 1.
Sorry.
B1 into 2 to the power plus 1.
So making this mistake again. Sorry, plus 1. B minus 3. So I substitute these values. So minus 1 into 2 plus 1 into 1 plus 0 plus 1 into 2 to the power minus 2 plus 0. This will be minus 2 plus 1 plus 0.25, which is minus 0.75. So that is my actual Q of VA. So in decimal, the value is minus 0.7. Understood until this point how we are doing? So if I give you a Q format, you should be able to get this value by using this thing. Now again, this is in
Sir,
Q's complement.
how,
Yeah.
sir, how the 2's complement is making this B1 to be negative, sir, here?
Like it is not actually minus. You can say minus 1 into B1. So this 2's complement means there will be a negative term for the first bit, right? So minus 1 into the first bit, say some bx into 2 to the power x. So here minus 1 into bx is 1 and 2 to the power x is 1. So like let me take a dark color. So this is 2 to the power 0 term. This is 2 to the power 1 term. This is 2 to the power minus 1. 2 to the power minus 2, 2 to the power minus 3. So 2 to the power 1 into B1 into minus 1, 2 to the power 0 into B0, 2 to the power minus 1 into b minus 1, 2 to the power minus 2 into b minus 2, 2 to the power minus 3 into b minus 3. Substituting this in this expression, I am getting this. Had it been straight binary, this minus 1 will
once
not be
again.
there, it is plus 1.
Sir, minus 1 is a syntax almost, sir?
Yes, yes. So
Okay,
this
for
is coming
any
because
numbers,
of
when
2's
you're going to
complement.
change it NX to Q format, minus 1 we can add it.
Yes,
It's
because
not
it is
related to
2's
2's complement. Okay.
If it is straight binary, so as you are asking, say for 2's complement, this is the value. Say for straight binary. For straight binary, what will be my expression? B1 into 2 to the power 1
directly.
Yes, 2 to the power 0. B1 into 2 to the power minus 1. B2 into 2 to the power minus 2 plus B3 into 2 to the power minus 3. So my binary, which representation I am using, that decides my sign here. So now it becomes 2 plus 1 plus 0 plus 0.25 plus 0, which means 3.25. So in straight binary, it is 3.25. In 2's complement, it is minus 0.75. Whereas in offset binary, it will be a different value that you can do, because from offset binary, you can convert into 2's complement by making this inverted. So that I'm leaving as a homework for you. You can do that for offset binary. So this is how a Q format works. Now, if there are two different Q format numbers, how do I add them? So every time when we are adding two Q format numbers, say I have given you, let me choose it. Say Q1.4, Q2.5. How do I add? I have to first convert this into Q2.5 and I have to convert this into say 1.6. So now I have to convert this 1.6 into 2.6 and this 2.5 into 2.6, and then only I can add. So I can add only when the Q formats are same. Say this is Qn1.m1 and this is n2.m2. The final one is say Q2.6. So 2 is maximum of n1 and n2, and 6 is also maximum of m1 and m2. So n will be maximum of n1 comma m2, m will be maximum of m1 comma m2. So when there are two two different Q format numbers, and when you are adding them, then you have to maximize the n and m, and then only you can add. So now the question is, how do I change the Q format from 1.6 to 2.6 and 2.5 to 2.6? So whenever you are increasing the LSBs, you can pad with the zeros. And whenever you are increasing the MSBs, you have to pad with the MSB only. So for this, we'll come to an example. Say padding LSBs. So from Q2.2 to Q2.3, I can put a 0 at the end and the value remains unchanged. So let us check whether the value remains unchanged or not. So this is 2 to the power 0, 2 to the power 1, 2 to the power minus 1, 2 to the power minus 2. So its value will be minus 2 plus 0 plus 0.5 plus 0.25. So its value is minus 1.25, right? Can you please check if this value is calculation is right or not? This is right? You have understood how I am doing this?
Yes, sir.
Yeah. Now for this I am doing. So minus 2 plus 0 plus 0.5 plus 0.25 plus 0. Because 0 has no value, the value is bound to be same. 2 to the power 1, 2 to the power 0, 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. As adding a 0 at the end doesn't make sense because we can add n number of zeros. But for our Q format, I am adding a 0. Now Q2.2 become 2.3. Okay, so whenever we want to increase the LSB, so from 2.5 to 2.6, if I want to add, I will add a 0 at this number. But what if I have to add MS space? How will I do? I will not add 0 because that will completely change my value. Adding the 0 will completely change. So how to do? Say 1011 is there. I will add the MSB. So whatever MSB is there, I will add the same MSB. Now the question is, will the value remain same? Let us find. So this is 2 to the power 1, 2 to the power 0, 2 to the power minus 1, 2 to the power minus 2. So whatever value that we got, it will be the same, which is minus 1.25. Now we have to find whether the value will remain changed for this 3.2 format. So this is 2 to the power 2, this is 2 to the power 1, 2 to the power 0, 2 to the power minus 1, 2 to the power minus 2. So it is minus 4 plus 2 plus 0 plus 0.5 plus 0.25. So this is minus 2, this is 0.75, value is minus 1.2. So without changing the value, if I want to change the Q format, if I want to extend the LSBs, I will pad zeros. So I will pad zeros if I want to extend LSBs. But if I want to extend MSBs, then I have to pad the MSB only. Say what will be the Q 5.2 format. So I need 5 such bits. So I have to add 3 MSBs. So 1, 2, 3 MSBs, 1, 0 and 1, 1. If you find the value, it will be minus 1.25. I am not doing it. I want you to do it. So you can do. Here if I want Q2.5, I have to add 3 zeros, 1, 0, 1, 1, 0. Again, if you see, I am writing underscore. You can write this underscore in Verilog code. This will not do any difference in the code, but this is for our representation. That is a dot. So for our representation, that this is a dot. So before the dot, it is 2 to the power 0, 2 to the power n. After the dot, it is 2 to the power minus 1, 2 to the power minus 2. So we are putting this as a virtual dot. But in the code, it will be 1011. So the Verilog simulator will take this as 1011. This is 10110. This is only for our understanding. So I'm writing. So Q format is only for our understanding. And this virtual dot is also only for our understanding. There is no virtual dot in FPGA. So this is only for our understanding. So that we can get that quantized voltage. So let me go back once here. So here I want to get the quantized voltage without doing this multiplication. So I have put a virtual dot. So if you consider 1100, you can directly get the quantized voltage. So in this case, if all of them are 1.111, then you can calculate say 1.000. So this is the maximum negative voltage, which is minus 1 volt. If you consider 0.111, this will be the maximum positive voltage, which will be 0.5 plus 0.25, which is 0.75 plus 0.125, so 0.875. So this is the maximum voltage. If you remove dot and substitute here, you will still get the same value. Say 0.111, which is 7 into V span by 2 to the power 4. So it is 7 by 8. Sorry, 0.875. So instead of doing all this, I am forming in such a way that I will keep a virtual dot, and directly by calculating the value, I am getting the value like actual analog quantized voltage instead of doing all these things. So I am just putting a virtual dot, so I will get to know what is my quantized analog voltage at any point. So that is the main intention of Q format. The main intention of Q format is to find the quantized analog voltage at any given point of time. So we want to find the quantized analog voltage at any given point of time. So using this virtual dot, I'll keep the dot. I'll then see 2 to the power 0, 2 to the power, and then I'll find the value. If it is 2's complement, it can be negative. If it is straight binary, it can be only positive. So this is all about addition of Q format. Now coming to the multiplication. So when I'm multiplying n1.m1 with n2.m2, as it is multiplying, the number of bits will get added up. So if it is 5 bit and this is 6 bit, it will be 11 bit. So n will be n1 plus n2, m will be m1 plus n2. We are dealing with 2's complementary, right? So 1 bit is for binary. Sorry, 1 bit is for sign. So here it has 1 sign bit. Here it has 1 sign bit. And how many does this need for sign bit? 1, right? So it also need 1 sign bit. But we are adding 1 plus 1, 2 sign bits, which are redundant for sign. We only need 1. So Q n.m has 2 sign bits we don't want. So we can reduce the MSB and we can add a 0 at this end. So 1 extra bit you can add, which means we are padding 0, because for LSBs, if you want to extend, you have to pad 0. And the most significant bit we can remove, because there are 2 sign bits and which are redundant, and we need only 1 sign bit. So one signed bit should be enough. So in the case of multiplication, we will get one extra bit, which is a redundant bit. So we'll remove that. So we are removing the MSB bit, most significant bit, which is redundant, and we'll add a 0 for to maintain the overall number of bits. So you can use that 0 for improved resolution or for any other purpose. I hope this part is clear until this point.
Yes. Sir,
So-
how the
Mhm.
sir, how two sign bits arises in Qn.m?
Say Q1.2, Q 2.1. Say this is 1 0 0. This is 0 1 0 0. Now let me use another color. This is sign bit, right? So this represents sign, whether it is positive or negative. It also represents sign, whether it is positive or negative. And how many bits do I need? Only one bit. So in Q 3.3 also, if you multiply 1 2 3 underscore, this is underscore with the thick line, and 1 2 3. So I am getting two sign bits which are redundant. Instead of this, I need only one sign bit. Understood? So what I was trying to say is
Sir, the both the bits are the same. That is what we're trying to say.
yes. So we don't need this additional bit to represent the sign. So we can remove this. This is the most significant bit. So we can remove this and only consider these bits. And now we have removed one bit. You can pad a 0 for resolution so that you can utilize all the number of bits. So that's what we are saying. As it is two signed bits. Yeah. We need only one signed bit. So we can remove that additional. So with this being cleared, we can move on to our next topic, which is the counter-based DPWM. So we have discussed in our second week, we have discussed that in the case of analog, our PWM will be like this. So I can say this is analog, which is like a ramp, smooth ramp, and it is being compared with the, say, this is VRAM and this is VCon. Now, in the case of digital, I have told you that it will not be like smooth. Instead, it will be like a staircase. So we use a counter. So it will count from 0 to whatever that value is 2 to the power n minus 1. And then we are being, it is being compared with, or maybe I'll use a red color only. So now it is being compared with. So now this VR is RAM is digital, and this VCon is also digital. So this is digital, this is analog. Here it is smooth RAM, here it is staircase. So this is the counter-based DPWM. So we'll check Verilog HDL. If time permits, we'll go Xilinx ISC, else we'll proceed to the problem. So in the counter-based DPWM, so this we have discussed in our second week, so I'm not spending time. I'll quickly go through the Verilog implementation. So this is the counter-based DPWM. So we are having a staircase from 0 to nr minus 1. And how many such staircase will be there? So the total number will be 2 to the power n, from 0 to 2 to the power n minus 1. So the total will be 2 to the power n. So 2 to the power n into t clock, 2 to the power n into t clock will be TSW, or f clock is 2 to the power n times FSW. So this we have discussed in second week. If you still have doubt, you can go through SARS lecture, or you can go through week 2 session of mine. So f clock is 2 to the power n FSW. And we have discussed the resolution will be 1 by 2 to the power n. So if you want to improve the resolution, you have to use higher clock, as T clock will reduce. So QD is dependent on two things. One is T clock, TS. So if you want QD to be less, which means high resolution, so the error margin will reduce. So if I want high resolution, I have two ways. Use different color. So I have two ways. First way is I will reduce the T clock, which means clock frequency should increase, or my n should increase, which means ADC number of bits should increase. So for a given FPGA, say in our case, Spartan speaks 6 FPGA, F clock is 100 megahertz. So you cannot increase the switching clock. It is decided by the FPGA that you have bought or that you are using. So you can only increase N. Again, increasing the ADC number of bits will increase the cost. So again, there is a trade-off. We are using 10 bit, which is equally good. So the resolution is 1 by 2 to the power 10. I think it is 10 millivolt or 20 millivolt or maybe 2 millivolt. I'm not sure. We'll check. So it will be very less and it is working fine. It should work fine. 10 bit is decently high. So this is about counter-based DPWM. So what SAR is exactly doing is, so here you have one counter. So you can consider this as counter and this as controller output. So SAR is increasing a counter and making sure whenever this controller output is more than counter value, then output is 1. Else it is 0. So this is the simple logic. So I can put a comparator if you want. So one being the controller output and other being the counter. So whenever controller output is high, that will give me Q. So this digital control, this is a comparator, right? So this is a comparator. So in analog, comparator means there is a different IC. In the case of digital, comparator means you can simply write if A greater than B, Q equal to 0. Else, or say Q equal to 1. Else, Q equal to 0. So this is a digital comparator. A and B are being compared. So if A is greater than B, say this is A, this is B. If A is greater than B, Q is 1, else Q is 0. So digital comparator is just few lines of code, whereas in analog you need a separate IC. That is one advantage of digital. Things can be much simpler. Also, it comes with additional difficulties like resolution, everything, finite resolution. So here we have counter as well as controller output, which is going to comparator and it is going to QPWM. So counter-based DPWM. So there are again two things. So this entire thing is the code, but this entire part will not be currently you might not be able to understand because this will be detailed taught in digital voltage mode control, which is in week 8. So only this is our concern. This is our counter-based DPWM. So even if you do not understand the left part of the code, it is okay because it is not yet taught. It will be taught in the upcoming week, but you should understand this part of the code. But still, I'll explain it. So it has clock, FPWM, controller output, QH, QI. QH is the high side gate pulse, QL is the low side gate pulse. Inputs are clock and FPWM. And controller output is coming. Say again, this has some Q format. We'll go into the details of this in the next week. Currently, just think in this way that there is some Q format that we are going to use. Why it is 4.15, how it is coming, we'll discuss detail in the next week. SAR will also teach. So outputs are QH and QL. As you can see, this is a vector. That's why we are defining it in next line. This is scalar. So that's why we are defining it separately. And outputs QH, QL, and there is a wire and another register SAR has used, another shift register SAR has used, and some other register PWM delay SAR has used. Let us not go into the details why SAR has used. That will come in the next week. But assume that these have been defined and this is a 12 bit. So Q format 4.8 and here it is 4.15. So what SAR is doing? SAR is discarding the last 7 bits. So that is what SAR is doing here. So SAR is considering the first 12 bits that is going into the controller output. So even if you have not understood for the time being, let us leave it. But just think that we need a counter and we need a controller output. So controller output, we got it from here. So what SAR is doing is for every posage of clock. So let us go back here. Let me use a different color. So for every posage of clock, so for every posage of clock, SAR is incrementing the counter. So for every posage of clock, counter should be incremented. So if counter is less than or equal to 1, QPWM is 1 and counter is equal to counter plus 1. So SAR is saying that if counter value is less than 1, so counter value, if it is less than 1, so QPWM is 1. So that is the minimum QPWM that SAR is feeding. So if it starts with 0 and if it is less than or equal to 1, Q will become 1. So this is for minimum duty ratio, SAR is giving this. Now, else if counter is less than or equal to controller output. So what SAR is doing, so now it is being incremented until the counter output touches controller output. SAR is incrementing the controller output. So SAR is making PWM1 as well as counter is incrementing. So SAR is incrementing the counter until counter becomes controller output, and this is always, so it will keep on iterating. So it will the loop will run infinite number of times. So SAR is checking. So if counter becomes controller output, then it will not enter this. So what happens else if counter becomes 499? So what SAR is doing is, here I have told you this relation, right? So SAR is doing this, that TSW or FSW is 1/500 times of F clock. F clock is 100 megahertz. So this will be 200 kilohertz. So SAR want a 200 kilohertz switching frequency for the converter that he will be running. So SAR is counting till 500. So from 0 to 499, this should come. So that's what SAR is doing. So SAR is resetting it. So after it reaches 99, QPWM should be 0 and counter should be reset. So after this point, what is happening? After this point, counter is being reset, right? So counter is being reset. And in the other cases, so one thing you should keep in mind is, so there are two regions. This is one region where counter will increment, and so counter plus plus. In case of C language, I can say counter plus plus. Counter is incrementing and Q is equal to 1. In this region, second region, counter plus plus and Q becomes 0. And at this instant, counter should be reset. So counter is equal to 0 and Q also 0. So this is the logic, and this is SAR's code. You do not have to copy the same code, but assume that this is the logic. You can implement it in. I can implement this in a different way. So according to your convenience, you can implement. But if you face any difficulty, you can refer to this. So whenever you are trying to implement Verilog, don't copy it. You try it by yourself. And when you are stuck at some point, then refer this. If you copy, then you will not learn. So this is the logic that we want. So try to write a code by yourself. And if you got stuck at some point, first try to resolve it. And if you realize that you are not able to resolve, then you can come here and you can check what is the difference where you are doing mistake. But if you copy it, then you will never understand the code. Even if I explain it, you might not understand the code. But I will not explain again, because until you do, it will not be clear. So like to find like summarize, this is the region. So in the region 1, counter will be incremented and Q will be 1. And this is the region where SAR is resetting. So counter is becoming 0 when counter is touches this. In other region, counter will increment and Q will be 0. So like this is the oral logic, but if you want to see whether this is working or not, I request you to try it by yourself. So, and this part, this will be coming in next week where I will explain. So this part should be clear. So this is about digital DPWM. Now coming to dead time circuit. You might know in the case of buck converter, this is the input stage, right? And this is the inductor, this is the capacitor. And here there is a load resistor. At any given point of time, both the switches should not be turned on, because if both the switches are turned on, input is shorted. It is a short circuit and high current will flow and MOSFETs will be gone. So they do something called break and make. So what they do is they turn off the high side switch, make it 0, and then only they turn on the low side switch. So first they break the circuit. So both the switches are off. Then what is the path? The diode is the path for the inductor. So they first turn off the high side switch and then keep it 0, and then only turn on the low side switch. So this is called break and make. So first you are breaking the circuit, or you can say breaking the path, and then you are making the path for inductor current, and until that time diode will continue. So the logic is as follows. Say this is the QPWM that you are getting from the digital PWM. Say from DPWM, you are getting this QPWM. You shift it by TD times. So let me drop this like this. Okay. Now we are shifting it by some time and we are doing the AND operation. So what we are doing? We are doing the AND operation. So QH is QPWM and PWM delay. So AND operation means when both are one, then only it is one. So when these both are one in this region. So only in this region we are getting QH to be one. So in this region QH is one. So not in this part as well as not in this part. So this part is QH is 0 because one of them is 0, and in this part also this is 0, so QH is 0. So only we are getting this region, in this region, and here also in this region. Now, and QL, what they're doing, QPWM plus PWM delay. So when QL becomes 1, when both are 0, then only QL is 1. So let me draw the line. I'll extend it. And I'll extend it. So if you see, we'll use this color. If before this, PWM is 1. So sum is 1 and QL will be 0. And after this, QPWM is 1 for some time. So output will be 0. So only in this region, or only in this region. So only in this region.
So we are taking OR, sir, right, sir?
Yes. So this
plus
is
represents
OR,
right?
and not. Here this is not. Like it is like QPWM bar dot PWM delay bar. So we are doing basically NOR operation, not of OR. So now if you see, this delay is coming in between these two, and at any given point of time, both are not on. So we are doing break and make. So we are breaking the high side pulse, and then we are making the low side pulse. So this is the logic. One of the logic. So is this the only logic to create that time? No, this is one of the logic that we are using. People use different logics, but we are not discussing. So this is the logic that we are going to use. And you can find any literature where they have mentioned different architectures. So how am I delaying it? So the main thing is delaying it. So one such way of delaying is passing it through multiple D flip-flops. So this will create one T clock delay. This will create another T clock delay. This will create another T clock delay. And this will create another T clock delay. So I am creating such multiple D flip-flops in series. So my QPWM with PWM delay will be delayed by 4 such T clock cycles. So the dead time circuit is as shown. So here SAR is using 6 such D flip-flops. 6 D flip-flops. So input is QPWM, output Q0 is shift 0. And if you see, these are all registers and these are all which statements, non-blocking statements. So this is shift 0, this is shift 1, this is shift 2, and this is shift 3. And in between we have shift 4 as well. So SAR has used 1, 2, 3, 4, 5, 6. So 6 such D flip-flops, or 5 such D flip-flops. As one is the input. So this is the input and this is the output. So this is 1 D flip-flop, 2, 3, 4, and this is the 5. So QPWM2 shift 0 is 1, shift 0 to shift 1 is another, shift 1 to this is another, this is another, 3 to 4 is another, 4 to 5. So 3 to 4 and 4 to 5. So I think we'll get 60 flip-flops only. Sorry. So there are 6 such lanes, so we'll get 6 D flip-flops. So 1, 2, 3, 4, 5, 6. So shift 3 to shift 4, we need another flip-flop, and shift 4 to PWM delay, we need another D flip-flop. Now my PWM delay I got. So what is the relation? Q high is Q PWM into PWM delay. So Q high is Q PWM into PWM delay. So this is the AND operation. This is the AND operation. And I need NOR. So I'll do OR and then I'll do NOT. So QL is NOT. So this is NOT and this is OR operation. So this is what SAR is using. So whatever PWM that SAR is getting QPWM. So SAR is using one delay block. So that SAR will get QPWM delay. And using this QPWM and PWM delay block, SAR is getting Q high and as well as Q low. Q high is AND operation and Q low is NOR operation. And the logic, first try to understand the logic and then try to implement in the Verilog. So this completes the dead time, but I will show the simulation now. Yeah.
So this in the OR operator, the double pipeline will be used if we are checking the condition.
Yes, yes. So there are two different things. Maybe I'll use this space. So one is the logical operator. Logical, or maybe it would be good if I discuss there only. Let us go to the operator. So one is the logical operator. Logical operator means it will be inside. So if A and B means if A and B is 1. So in logical operator only we use two ANDs. But in other cases we'll use single AND. So if you want C equal to A equal to C and B, we'll use single AND. So whenever you are doing AND operation, then you use single AND. But if you are using inside a logic, if A and B, which means if A and B is equal to 1. This is nothing but if A and B is equal to 1. This you can write in this way. So in logical operator only, we will use two ANDs. Else, in any combinational logic, we will use single AND. So here we are doing only combinational logic, so that's why we are using single AND. But if it is inside if, then we can use two ANDs. So this is the PWM delay part. Please try to go through SAR's lectures and understand how this is working. So I request you to draw these timing diagrams and see how the delay is being created and how we are doing the shift operation. So I request you to do the Verilog code writing, try to implement the code. The entire code is given here. You just have to copy paste, first try it by yourselves, and after if it is like if you are not able to get, then you can refer to this, but don't directly copy and do it, then you will not understand. So before we go into problem solving, let me just quickly simulate it. So I'll just try to show how that delay is coming. So let us go back to here, and this is the voltage mode control. So this is a part of voltage mode control which will be taught in the next week, but for teaching the digital what can I say, digital PWM, we are discussing in this week, but it will come in the next week where sir will be discussing in detail. So this is the DPWM dead time circuit. So it is just the copy paste of like the code has been copy pasted in the slides as well. So just to tell you, so the first part of the code is this block, second part is this block, continued by this block. So I humbly request you to simulate it, then only you will understand. Else understanding the code just by reading is impossible. So let me rerun it. So I have to provide inputs and see whether that delay circuit is happening or not. So I have simulated it, and it needs certain inputs. So one input is clock, so force clock. I'll give 100 megahertz, which means 10 nanosecond. 10 nanosecond, enter. And FPWM, which means force clock say SR is using 200 kilohertz, which means 5 microsecond, 5 microsecond. And controller output, why we are giving this, let us not discuss, but for the time being, assume we have given some value and we are checking whether that block is working or not. So I'm giving what sir has given in his lecture. So it is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is how many bit? 19 bit. So we are giving 19 bit and we are giving the duty ratio in such a way that it will reflect the duty ratio in the QPWM. But how we are choosing this for the time being, let us not discuss because it will not come in this week, it is next week. So as my FPWM is 5 microsecond, I am giving 100 microsecond, which means 20 such cycles. I'm simulating it. And let me bring this down. So let me zoom in. So this is zoom in. So this you can use to take it anywhere. So let us put it in between, say here, and I'll zoom in. So this down means you will get another such vertical cursor. So now we have 2 cursors. So let me zoom in more. So if you see, this is my QL and this is my QH. So the difference between them is 60 nanoseconds. So how am I getting 60 nanosecond difference? So if you try to understand, here I have pointed out that these 4 flip-flops make 4 T clock. 4 T clock.
Nanoseconds.
Yeah, so here we have 6 D flip-flops, which means 6 T clock. T clock means 10 nanoseconds because 100 megahertz. So it makes 60 nanosecond delay. So that's how we are getting 60 nanosecond delay. So you have to understand this much because whatever code that you are writing, whether it is working or not, we should check. So this is 60. Here also it should be 60. So 60 nanoseconds. So and designing that time is another topic. So sir has discussed. So that time should not be very small because the switch should be off. Ideally, we think that switch will turn off, but switch will take some time. It has some fall time. So that time should be in such a way that we will give enough time for the switch to fall and enough time for the switch to rise. So at any given point of time, both the switches should not overlap. So now both are overlapping, right? So this should not happen. So we have to provide sufficient dead time. But if we increase the dead time, then what will happen? If we increase the dead time, then the diode conduction time will increase and it will create more losses than what is necessary. So we should not keep on increasing dead time. We should give whatever dead time that is sufficient, just slightly higher for safe side. But we should not give more dead time, which will be counter-effective to what our aim is. Our aim is to not turn on both the switches. So we will provide whatever is sufficient with some extra for safety, but not more. So, but how to design that dead time, that we will not discuss in this course, which is beyond the course syllabus. So now let us. So this
The dead time should be.
Yeah.
The dead time should be at least greater than the fall time of the switch, right?
Yes, fall time as well as like rise time. Considering fall time and rise time, accordingly you will make sure that dead time is sufficient so that both are not being overlapped. But you do not make it very close to each other because at this point you are not sure that if they overlap each other or not. So that's why we put some difference for safety, and we'll implement that in the Verilog code. But there are few gate drivers for which you give only QPWM and it itself will generate QH and QL. So in that case, you need to give only QPWM. That time will be generated by the MOSFET itself. But there are few MOSFETs where you have to give QH and QL. So you have to give that at time. So keep this in mind. And that designing that time, that is beyond the scope of this course. So, but you can refer to any literature or any data sheets or application notes where they have discussed how to design the data. So here today we have discussed Verilog code and then ripple carry adder, and then we have discussed binary numbers, and then we have discussed something called Q format, and then we have discussed digital PWM implementation. Now let us solve few problems. So the first problem is I have given some decimal numbers. I am asking you to write them in 5-bit straight binary, 2's complement, or offset binary. So what are the answers? Say this is straight binary, and this is 2's complement, and this is offset binary. Say this is straight binary, and this is 2's complement, and this is offset binary. Can you tell me what are the values for 0? It will be
Yeah,
0,
5 zeros.
5 zeros. So here also 5 zeros, and here also 5 zeros. Sorry. And for 6,
20110.
20110. So here also 20110, 20110, and 10. So
10 01010.
So as I have not given any signed numbers,
Sir,
so yeah.
when we
Offset
are writing
binary.
we are trying to write that. Okay.
um,
Sir, when we are writing the 2's complement,
mhm.
actually we have to take the 1's complement of this number and then add it with 1, right?
Yes,
That is the 2's
yes,
complement.
that is the 2's complement.
But if you take 00110 and if you take the complement and add 1, it will become 11010.
Let me check. So here 1, 2, 3, 4, 5. So the offset binary input will be 1 because it is the invert of 2's complement. So if you take 1's complement, 11101, and if you add 1, it will be 0, 1, 0, 0, 110. 11001, and then you add 1, 11010. Yeah, it should come, but why it is, say, no, I think that is only for the negative numbers, right? Not for positive numbers. Positive numbers, it will be same. For negative numbers, you do that. Understood? Hello?
Okay.
So that 1's complement plus 1,
Okay.
it is
So for the positive numbers, it is still
it
remaining.
is just the same, right? So this is for the negative
Okay.
numbers now. So for negative numbers, you do that and you will get it. For positive numbers, this is the
Okay.
case. So for 12, I think 0, 1, 1, 000, right?
Yeah.
So maybe I should have given
Sir, offset
negative
binary
numbers
is
also.
complement of
Offset binary, the most significant will be the complementary of 2's complement, right? So that's why here it is 0, so here it is 1. Here it is 0, here it is 1. Here it is 0, here it is 1. So for 15, I think it will be 0, 1, 2, 4 ones. 0, 1, 2, 3, 4. Here 5 ones. So if I give a negative number, then it will be accordingly changed. So now I'm asking what is the combinational logic of so this question is clear, right?
Sir, if you give a negative number here.
Yeah. So give me one negative number.
So -12 if you do.
-12. Okay. Yeah. So in straight binary we cannot write because it is not applicable. Okay. Let me change. Use some dark color. Yes. So -12. So first of all, here it is not applicable. And for this, how will you do? You invert this. So 0, 1, 1, 0, 1, 0, 1, add 1. So 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0. So now let me check if it is actually working or not. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So it is -16 plus 4, -12. right? Now it is working, right? The whatever logic we are discussing. One's complement plus is only for negative numbers. So I have taken plus 12. I have taken plus 12. I have inverted, taken one's complement 1 0 0 1 1, added 1, output 1 0 1 0 0. That is my minus 12, and I am cross checking whether it is giving minus 12 or not. Now in the case of offset binary, I will toggle the first bit is 0 0 1 0 0. And there is one small mistake here. It should be 1, because in offset binary 1 means it is positive, 0 means it is negative. In 2's complement, 0 means positive, 1 means negative. Offset straight binary is only for positive numbers. So that's how we do. So I hope this question is clear.
Yes, sir.
Now moving on to the next question. Can you tell me what is the circuit?
XOR. So what is half adder?
No, like it may or may not be half adder, but you
Not half
understood how I'm doing, right? So first X variable is XOR of A and B. Let me use a dark color. Maybe it is a half adder, or maybe it is not a half adder.
It has 3 inputs, so
yeah, we'll see. So A, B. So A and B are going to one first XOR gate, and output is X. And B and C are going to AND operation. So AND operation. This B is one input and C is the another input. So output of AND is Y. And now this is doing OR operation, which is my F. So you are partially correct. So this part is half adder. So this is half adder circuit. But I have added an additional OR block just to make it different from the half adder. So from the Verilog code, I understood what is my implementation of this. So I hope this question is clear.
sir, in half adder we won't be having third input, right?
No, sorry, you are right. Yeah, half adder we don't have third input. Then I think it is neither full adder nor half adder.
There's some logic.
Some other logic. Sorry, you're right. This is neither half adder nor full adder. If it is A or A XOR B and A B, then it is half adder. This is neither half adder nor full adder. So yeah. Now, if I do it the other way, say I have given you one logic, then I have asked you to write the Verilog code. How will you write the Verilog code? Can you help me? Say I'll write module, say some example circuit. So some example circuit. And first
Yep.
I'll define F, A, B, C.
Yep.
Then
A, B. Input.
ABC and
Input ABC. Output is F.
output F. Then maybe we'll take some variables, right?
Sir, now we have to do NAND and AND OR. All three
So
operations.
this is first operation is not, next operation is and here also and then we have to do OR. So first, so for not we need one variable, and we need another variable, and we need another variable, or we need another variable. So let us say wire x comma y comma z comma double. So first for not operation, what will be the code? Not some gate one x comma a.
Okay.
And for AND operation, how will I write?
The same, sir. And some gate and then
Gate to
B comma C.
B comma C. B comma C, and in output is say y, right? Y comma B comma C. So output is y, input is B comma C. And then we are doing this AND operation. So how will I write? Some gate 3, say W.
B comma X.
X comma A.
A.
Sorry, this should be B because we are inverting B, X comma A. Now final is the OR operation, gate 4. Output is F, summation of Y comma W. So there is less than a minute. If this meeting ends, please quickly join. So from this I can say I don't need W, so I need only X, Y, Z. Or X, Y, Z is not liquid, W, X, Y, W. So I need 3. So the same thing, F, A comma, B comma, C, input, output, I have taken X, Y, Z. First I have done NOT, then I have done AND, then I have done another AND, finally I have did OR. So that's how you do. So you can also start writing these codes in Verilog. If there is a less than a minute, there are 2 more questions. If this meeting ends, please join so we can discuss. So until this point, it is clear, right?
Yes, sir.
Yeah. For all of you, ma'am, until this point, is this clear, ma'am? Okay, then we'll go on to the further question, which is 4. We are in this question. So where we are, I'm audible, right?
Yes, sir.
Yeah. So here I have given span and I'm asking the quantized voltage. So the span is 1 volt given and 10-bit ADC. So we have to multiply NX with 1 by 2 to the power 10. So for the first case, what will be the answer? So for the first case, it will be 100 by 2 to the power 10. In the next case, it will be 238 by 2 to the power 10. So we have to calculate that what is that value by 2 to the power 10. And this is minus 256 by 2 to the power 10. So this is minus 0.25. So I have said it is 2's complement. So that's why it can be negative. So for 2's complements, for 10-bit, what is the value range? It can go from minus 512 to 511, right? So this is the range. Right? Rajshekhar, is that clear?
Yes, sir.
Yeah.
Sir, but the range.
So minus 512 means what? Minus 0.5 volts, right? 512 by
Okay, sir.
2 to the power 10. And this
Yes, sir.
means almost 0.5, maybe 0.499. You can consider 0.5 volts. So V span is 1 volt.
Okay.
Yeah, so this is how you get the quantized voltage. If it is 2's complement, it can be negative. If it is straight binary, it is only positive. So we are in the final question. So find the Q format. So what is the Q format of these things?
2.3, Q 2.3,
This one?
Q 1.4, Q 1.4, Q 1.4, and then Q 3.2.
Yeah. So now we found the Q format. If I ask you to find the values, so for A, what will be the value? Minus 2 plus 1. Right.
Yes, sir.
So this is minus 0.75. So the value is by 0.75. And for the second case?
Second case, 2 to the power minus 1. So 0.5.
Yeah, 0 plus 0.5, 0.5. So the value is 0.5. And for the third case?
1 minus 2.
No, minus 1. This is 2 to the power 0.
Yeah, okay.
Minus 1 plus
0.5
plus
0.5, 0.25 plus 0.125 plus 0.065.
0.625.
Yes, sir.
So whatever this value, with this I cannot calculate in my mind. So whatever maybe that value.
Yeah,
so
0.5 it is coming, sir.
It is 0.5.
Yeah.
No, I think it will be 0.0175 something, 275.
0.5.
I think it is.
Sorry, sir. Yes, sir. Okay.
I think it is 0.0625 or something. What is the value?
Yeah, if you add all the positive values, it is 0.9375.
Okay, so it is 0.0625, right?
Yes, sir.
And for the last case, it will be what? 0 plus?
Yeah. 0 plus 1 into 2 to the power 1. plus 1 minus 0.5 0.25.
0.5 plus 0.25. So it is
0.25.
3.75.
Yeah.
So these are the values. So here n is the integer bit, m is the fraction bit. So that's how we calculate the quantized voltage. So with this, we can conclude this session. So I'll just summarize what we have discussed. So first we have discussed introduction to Verilog, and then we have discussed different parts of Verilog data types, modeling, and different like data flow design, everything. And in the second, we have considered triple carry adder. We have considered Verilog plus simulation in ISC. We have seen how to simulate in ISC whether our logic is working or not. And then we have come back to binary numbers. So what are the different representation of binary numbers, mainly 2's complement, offset binary, and straight binary. And then after binary numbers, we went to fixed point arithmetic or Q format, which is very crucial. And we have discussed how we are getting the Q format, what is that virtual dot, and what is its analogous quantized analog voltage. And then after Q format, we went to digital PWM, DPWM, and which is counter based. And for this, we have also checked Verilog implementation plus ISC simulation. And then finally, we have did some problem solving on the concepts we have discussed in this. So if you have any doubts, you can ask me, else you can end this session here. Do you have any doubts?
Sir, this power, if you can, actually I have asked for that buck converter, power circuit, and signal conditioning circuit PCBs.
Okay.
If you can purchase from you, we can do it, sir.
Yeah,
Otherwise,
again, I told you like this depends upon SAR. So you should contact SAR. If SAR's email is available in the course, then you can contact SAR, or you can get SAR's email
at least
videos.
At least some videos of how to make that can be helpful also.
Like videos, if we are talking about a board, so it is related to some PCB software. So making a video is difficult. So, but asking you to learn PCB also difficult. We understand, but again, if SAR is willing to sell all those things, that depends on SAR, because like it is finally SAR's decision. So you either contact SAR in the upcoming YouTube
live
session,
sessions,
or you can mail SAR regarding this. So SAR will see if SAR can share, then SAR will share. Else we cannot do anything there. Then you can ask SAR for any other choice. So you can talk to SAR.
Okay.
So if you don't have any doubts, we can end this session. Thanks.
Yes, sir. Thank you, sir. Thank you, sir. Good night, sir.
Good night.